A scalar quantity is going to be just a number. A vector quantity is going to be a number and a direction. For example, distance is scalar, but displacement is vector because it's distance in a direction. Mass is scalar, but weight, which is your mass upon the earth, is vector. Speed is scalar, but velocity, which is speed in a certain direction, is vector. Acceleration and force are both vector, and momentum is also vector. Distance equals speed times time. Distance is measured in meters. Speed or velocity is measured in meters per second. Time is measured in seconds. Distance time graphs tell us lots of information. If we have a slope that is increasing, we are moving. And the steeper the slope, the faster we're moving. If it is a flat line, it is not moving. We can see that as time is increasing, our distance is not increasing. So in a distance time graph, the flat bit is not moving. We can calculate speed as the gradient. Gradient is up over across, which is going to be distance over time. Velocity time graphs look very, very similar to distance time graphs, but are different. For example, at our flat bit here, it is now moving, but it is going at a steady speed. We can see that when they are increasing, they are accelerating. So we now know that acceleration is equal to the gradient. That's up over across, or velocity over time. If we want to work out the distance travelled, that's the area under the graph. For this section here, it is a triangle. So to work that out, it's going to be half times base times height. For this section here, that is a rectangle, so that is going to be base times height. This section in the middle here is a bit more complicated because we have a triangle, a rectangle, and a triangle. So that is base times height plus half times base times height, and the height is the height of the triangle there. To work out acceleration from velocities, we have acceleration equals final velocity minus initial velocity over time taken. Velocity is measured in meters per second, whether that is final or initial velocity. Acceleration is measured in meters per second squared, and time taken is measured in seconds. Final velocity squared minus initial velocity squared is equal to 2 times acceleration times distance. Velocity, final and initial, is measured in meters per second. Acceleration is in meters per second squared, and distance is in meters. The value of gravity depends on where you are. The value of gravity on Earth is 10 newtons per kilogram, where on the moon the value of gravity is much less, which is why it looks like they're bouncing around on the moon. However, if you are falling on Earth, we can say that your acceleration due to gravity is 10 meters per second squared. Same number, different units. If we're looking for the resultant force, we need to find the difference between them. For example, here we have 10 plus 10 newtons minus 5 newtons is going to give us plus 5 newtons, which is going to be 5 newtons in that direction. For the second one, we have plus 2 newtons minus plus 2 newtons, giving us 0 newtons as overall resultant force, so there is going to be no movement. Force equals mass times acceleration. Force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. Don't want to overload you with too much maths, but there is a bit more coming, so just take a tiny little break. Your weight is not the same as your mass because your weight is equal to your mass times gravity. Your weight is measured in newtons, your mass is measured in kilograms, and gravity is measured in newtons per kilogram. So your mass will never change, but your weight will change depending on the planet or depending on gravity, which is why when they went to the moon, they were basically weightless so they could jump around. Centripetal force is just the resultant force when things are moving in a circle. So if we have our centre of a circle here and our object here, it is moving in this direction, except it's being forced round into a circle here, here. But at each point, what it wants to do is to move in a straight line. However, it's being forced around in a circle. And because it's being forced around a circle, we can see it has a constant speed but changing velocity, because velocity is speed in a certain direction. Momentum is mass times velocity. Mass is measured in kilograms, velocity is measured in meters per second, and the momentum is measured in kilogram with a space meters per second. I know there's a temptation to put another line in there, but that would be wrong. The law of conservation of momentum says that momentum is always conserved, which in calculations means your momentum before is going to equal your momentum afterwards. So if you have two objects colliding, their momentum together before is equal to the colliding combined object afterwards. We can say that force is equal to mass times final velocity minus mass times initial velocity over time taken, where force is measured in newtons, mass is measured in kilograms, final velocity in meters per second, mass again in kilograms, initial velocity in meters per second, and time taken in seconds. Stopping distance for a car is going to be made up of two things, thinking distance and braking distance. And you can see that the faster you're going, the more the stopping distance and the thinking distance increases. This is because for thinking distance, your brain needs to firstly see the image, the signal needs to get sent to your brain, needs to be processed, and the signal needs to get sent all the way down to your foot. And the faster you're going, the more distance you'll travel in the time that takes. Things that affect thinking distance are going to be drinking alcohol is negatively going to affect it, taking illegal drugs is negatively going to affect it, but taking something like caffeine is going to positively affect it. Tiredness is going to negatively affect it. Things that are going to affect braking distance are the conditions of the tyres. So nice new tyres are going to stop much quicker than old tyres which don't have much grip on the road. The condition of the road, so a snowy, icy road is going to have much longer braking distance than a new road, or a road that has a lot of grit on it is also going to have a long braking distance. And the weight of the car. A heavy car is going to take much longer to stop. To work out kinetic energy, that is half times mass times velocity squared. With kinetic energy being measured in joules, half is just a number, so we don't need units for that. Mass is measured in kilograms, and velocity is measured in meters per second. And it's important to note for this one that here is just the velocity squared, not the whole thing. To calculate work done, that is force times distance. Work done is measured in joules, force is measured in newtons, and distance is measured in meters. And from this we can say that 1 joule is equal to 1 newton meter. The different types of energy can be remembered by using Geek's Lunch. I would admit the U doesn't stand for anything. Gravitational potential energy, electrical energy, elastic potential energy, kinetic energy, sound energy, light energy, nuclear energy, chemical energy as in batteries or food, and heat or thermal energy. You'll notice most of these involve more than one type of energy. For example, in the phone we have electrical energy going in, but we have chemical energy being stored, and then heat energy because your phone gets hot, light and sound energy coming out. With the match we have chemical energy being stored, and then kinetic energy being used to strike the match, and then heat, light and a bit of sound energy coming out. With the fireworks, it was stored as chemical energy, and then we are going to have it transferred into kinetic energy as it moves up. As it explodes, we're going to have light, heat and sound energy coming out, and then gravitational potential energy as it starts to fall, kinetic energy as it falls back down. The law of conservation of energy tells us that energy cannot be created or destroyed. It is only transformed into another type of energy. Which is really cool because it tells us that the energy you're going to have for lunch or breakfast today has been around since the start of the universe. That the energy that's powering your computer, your phone, your lights has been around since the start of the universe. And the energy that you are using, the kinetic energy, the chemical energy that you are using today to get out of bed, to do your daily things, is going to be around till the end of the universe. If we want to work out the change in gravitational potential energy, that is equal to mass times gravity times the change in height. Gravitational potential energy is measured in joules, mass is measured in kilograms, gravity is 10 newtons per kilogram, and height is measured in meters. To work out kinetic energy, that is half times mass times velocity squared. With kinetic energy being measured in joules, half is just a number, so we don't need units for that. Mass is measured in kilograms, and velocity is measured in meters per second. And it's important to note for this one that here is just the velocity squared, not the whole thing. While energy cannot be created or destroyed, it can be wasted. Wasted energy is any energy that comes out of a situation that we didn't intend for it to be there. For example, in a light bulb we have electrical energy going in. This is converted into light, heat and sound. The light is the useful energy, whereas the heat and the sound are not useful energy, they are wasted energy. And a word the exam would love to describe this, if we can say that the wasted energy dissipates into the surroundings. It spreads out so much it can't be collected and used. It's not gone, it's still there, it's just spread out, it's dissipated. When we want to visually show the efficiency of something, we can use a Sankey diagram. So on this side we have the energy going in this direction is the useful energy, and this direction is the wasted energy. So in our example here of a blender, the energy going in is going to be electrical energy. The useful energy coming out is going to be kinetic energy, and the wasted energy coming out is going to be sound energy. Now the reason I've switched to graph paper for this is because we can put numbers on it. We have 20 squares going up that way, and that could be 20 joules. 15 squares going this way, and that could be 15 joules. And 5 squares going that way, and that could represent 5 joules. The units might change for this, but what the key thing is, you need to count the number of squares, assuming it's on graph paper, or if they ask you to sketch it, make sure it is roughly in proportion. Heat comes off and we can detect that with an infrared camera. We can see how well the house is insulated. The blue parts, the roof, are very, very cold, so not much heat is escaping. Whereas the walls here and here are very, very hot, so lots of heat is escaping. We can see that the roof is blue and the windows are blue, suggesting they're very good insulation. New houses are built to be very energy efficient, and old houses can be adapted to be very energy efficient. So we can have cavity wall insulation, double glazing, loft insulation, carpets, curtains, draft excluders, if they still have them, they could have a jacket around the hot water tank. Efficiency is equal to useful power out over total power in, and this can be a percentage or a decimal. Efficiency is equal to useful energy out over total energy in, and this can be expressed as a percentage or a decimal. When we're thinking about generating electricity, we can either do that with a renewable source or with a finite source. A renewable source is one that isn't going to run out and we can get more of it, whereas a finite source is going to run out. Renewable sources include things like the sun, the wind, water including tidal power, hydroelectric power, wave power, geothermal power, whereas a finite resource is going to be a fossil fuel, so coal, oil, gas or nuclear power. The advantage of solar power, the advantage of the majority of renewable resources, is that they don't release carbon dioxide. We're never going to run out of them, and they're generally non-polluting. The disadvantage of solar is that it doesn't happen during night and it isn't very good on cloudy days or wintry days. It can also be expensive to install. Wind turbines, a disadvantage of wind turbines is that some people don't like them. They also don't work very well on non-windy days. Tidal and wave power can be disruptive to the local environment, whereas a hydroelectric dam involves flooding a large area, which may include people's homes or animals' habitats. And the disadvantage of geothermal power is that it can only be used in volcanic countries. The advantage of using fossil fuels or nuclear power is that they are very, very readily available. It's a very, very cheap source of electricity, and things like coal power stations have a very short startup time. The disadvantage of using coal, oil and gas is that they take millions and millions of years to create, so we are about to run out of them. They are very, very heavily polluting, so they release large amounts of carbon dioxide and other pollutants into the atmosphere, which contribute to climate change. The disadvantage of nuclear power is that you have to store the nuclear radioactive waste for long periods of time, and there is a very small, but there is a potential risk of explosion. Here we have a longitudinal wave where we have areas of compression and areas of refraction. We can measure the wavelength in this from one point to another point. The direction of movement is side to side. And so it's the direction of energy. A transverse wave goes up and down from one point to another point, and this doesn't matter whether it's from the top to the bottom, from the middle to the middle. We have the wavelength. The amplitude is measured from the middle to the top or from the middle to the bottom. The direction of movement for this is up and down. This could also be the direction of oscillation, and the direction of energy transfer is sideways. Frequency is the number of waves per second. So if we look at this block here as a second in time, something that will have a low frequency, we are not going to see many peaks in 1 second. But something that had a high frequency, we would see lots of peaks or lots of waves within 1 second. You'll notice that for the high frequency one, it has a low wavelength, whereas for the low frequency one, it has a high or a long wavelength. If we want to measure the speed of a wave, we can use a ripple tank. This here will go in and out of the water, creating waves. From this we can measure wavelength and also looking at how many waves pass a certain point in a second, frequency. Then we can use our equation to work out the speed of the wave. V equals F times lambda. To work out the speed of a wave speed, we can take the frequency and times it by the wavelength. Our units for speed are in meters per second. Frequency is in hertz, capital H, lowercase z, and wavelength is in meters. Refraction happens when a wave passes from one medium into another medium, say from air into glass or air into water, and it will change direction. So here is our normal, here, move it down to here. It will change direction as it goes through there. And the reason it changes direction is because the wave changes speed, but different parts of the wave change speed at different points. So this part down here that hits first is going to change speed, either getting faster or slower before this part of the wave up here, which hasn't changed medium or speed yet. Using a prism or water in this circumstance, visible light can be broken up into its different parts. red, orange, yellow, green, blue, indigo, violet. Red light is going to have a wavelength of 7 times 10 to the minus 7 meters, moving through to violet, which is going to have a wavelength of 4 times 10 to the minus 7 meters. Frequency, we're looking at the other way around, so the frequency of red light is going to be 4 times 10 to the 14 hertz, whereas indigo is going to be 7 times 10 to the 14 hertz. Here we have the electromagnetic spectrum from radio waves, microwaves, infrared, visible light, ultraviolet, X-ray and gamma rays. Over here these ones are high energy and these are low energy. These are going to have a high frequency and these ones a low frequency. These are going to have a short wavelength and these are long wavelengths. Wavelength for radio waves can stretch into the meters, the kilometers, very, very long wavelengths. Our radio waves can be used for radio communications. Microwaves can be used for mobile phones and for heating food. Infrared are used for things like the button, the light on your remote control. You can also use it for heat sensing. Visible light is used for cameras in your eye. Ultraviolet can be used for detecting things like fake money. X-rays are used for broken bones, and gamma rays can be used for treating cancers or sterilizing things like killing bacteria. An atom is incredibly tiny. The word atom means uncuttable, and it's so tiny that the Greeks who named it an atom thought it was the smallest thing, but it isn't the smallest thing. We know there are things inside of it. Now, I said it was incredibly tiny. Its size is 0.1 to 0.5 nanometers, which is 1 times 10 to the minus 10 to 5 times 10 to the minus 10 meters. Now, inside our atom, we have protons and neutrons, and in the shells on the outside, we have electrons. This bit in the middle here, this is called a nucleus. Protons and neutrons are located in the nucleus, whereas electrons are in the outer shells. Protons have a mass of 1, neutrons have a mass of 1, and electrons are incredibly tiny. Their mass is 1/2000th that of mass of a proton or a neutron. Protons have a charge of +1, neutrons have no overall charge, and electrons have a charge of -1. Here we have boron. The mass number is 11. The atomic number is 5. So if you want to find the number of neutrons, that is mass minus atomic. 11 minus 5 gives us 6. Protons equal 5. Electrons equal 5. Now, protons have a positive charge, 1, 2, 3, 4, 5. Electrons have a negative charge, 1, 2, 3, 4, 5. So an atom, and this is for an atom only, will have the same number of positive charges and negative charges, which means there is going to be no overall charge in an atom. An ion is going to have lost or gained electrons. So for example, if we have take our boron again with our 1, 2, 3, 4, 5 positive and 1, 2, 3, 4, 5 negative charges, if it loses an electron, it now no longer has the same number of positive and negative charges, so it's going to be charged. It has created an ion. On the periodic table, you will see two numbers. The larger number of the two is the mass number. The smaller number of the two is the atomic number. It does not matter where these are located. Different books, exam boards are going to put these in different locations. It does not matter where these are located. The mass number is equal to the number of protons plus the number of neutrons. The atomic number is equal to the number of protons and also equal to the number of electrons in an atom. So if you want to find the number of protons, that is equal to the atomic number. Whereas if you want to find the number of neutrons, that is equal to the mass number minus the atomic number. There are three types of radiation: alpha radiation, beta radiation, and gamma radiation. Alpha radiation is also known as a helium nuclei. Beta radiation is also known as an electron. And gamma radiation is part of the electromagnetic spectrum. It's a wave. A helium nuclei and alpha radiation can be rewritten as alpha 4 mass of 2, positive charge of mass of 4, positive charge of 2. An electron can be written as E, mass of 0, charge of -1, and gamma is again just a wave. Alpha radiation is very large, whereas gamma radiation is very small. Alpha radiation is highly ionizing, whereas gamma radiation is not. Ionizing means how good it is at knocking electrons off, so how good it is at turning something into an ion. Gamma radiation is highly penetrating, whereas alpha is not. To stop alpha radiation, a bit of paper or a bit of skin will do it. Aluminium foil or thin foil will stop beta radiation, but thick lead is needed to stop gamma radiation. A Geiger millitube will measure radiation. It generally clicks every time it hears a bit of radiation. And the unit for radiation is the becquerel. Here we have two isotopes of carbon. You can see they have the same atomic number 6 but different mass numbers, which means each of them is going to have 6 protons. They are each going to have 6 electrons, but when it comes to the mass number, one of them has 12 minus 6, 6 neutrons, and one of them has 14 minus 6, 8 neutrons. An isotope is an atom that has a different number of neutrons. You need to know all of the different sources of background radiation. Now, the majority of background radiation comes from radon gas. This is about 50%. And this picture here shows a beautiful scene from down in Cornwall, down in Devon, because that area has a lot of radon gas going on. Then we have medical, and about 14% comes from medical x-rays, from different medical treatments such as x-rays or CT scans. Then we have stuff that comes up from the ground. This again is about 14%. Then we get slightly smaller, and these are the sort of things that you really can't avoid because you do get some background radiation from food and drink, and this is about 11.5%. Moving on to slightly smaller amounts now. Cosmic radiation, radiation that we get from space, is going to be about 10%. Even smaller amounts now from testing of nuclear weapons, it is going to be about 0.2%. from plane travel, and this obviously varies between person because the more you travel on a plane, the more radiation you are going to be exposed to. And then the last one, we're all going to get a teeny tiny little dose from nuclear power stations. And those are your sources of background radiation. The model of the atom has changed a lot over time, and it's changed because we have new developments and new discoveries. From ancient Greece, where they developed the word atom, uncuttable, to Dalton, where it was a solid sphere, J.J. Thomson, who discovered the electrons, where we had a plum pudding model, a positive sphere with negative bits dotted through it, Rutherford, who did the plum pudding experiment and worked out that it had a solid centre, Bohr, who developed the nuclear model of the atom. Now I know the writing is very small on here, that's because you don't need to know the exact details, you just need to know the overall development. Rutherford gave us the positive centre, which we call the nucleus. Chadwick added in neutrons, and then Bohr developed this nuclear model that we use today, with a positive centre and electrons orbiting outside. Rutherford wanted to test the plum pudding model, which was a large positive blob with negative bits dotted throughout it. So he took a sheet of gold foil and a gun that fired alpha particles, and he shot them at the sheet of gold foil. Now the majority of these particles went straight through, but very occasionally one would get deflected a little bit, and then even more occasionally one would get deflected a lot. And this told Rutherford that instead of it being an evenly distributed pattern of negative and positive charges, we are likely to have an overall build-up of positive in the middle, with negative charges around the outside, so that the majority of the atom was made up of empty space, and this led to the development of the nuclear model of the atom. Half-life is the time it takes for half the radioactive atoms to decay into something else. We can use that as a graph if we take 100% and 50%, read across with a ruler and down, 50%, cross with a ruler and down, and that there, the time between having 100% activity and 50% activity, or whatever value, and half of whatever that value is going to be the half-life. The half-life of something can range between very quick milliseconds to thousands, hundreds of years. The calculations for this are a lot simpler than they look. Here we have uranium-238. It is going to go alpha decay. Alpha is 42. So we have 238 minus 4 gives us 234. 92 minus 2 gives us 90. Then we need to use the periodic table to look up what has an atomic number of 90, giving us thorium. For beta decay, we have minus beta, 0 minus 1. 238 minus 0 gives us 238. 92 minus 1 gives us 93, which gives us neptunium. It does not matter about the mass number for these calculations, the atomic number is the important thing. Different isotopes of an element are going to have different half-lives. Awesome work for making it to the end, guys. I know this video is a slug to get through. The rest of this is physics only. We can use echo or ultrasound to determine distance, and we can do that because speed equals distance over time. So if we know the speed of the wave, we can measure the time taken and we can calculate the distance. So a vessel exploring the sea can send down an ultrasound and measure the time it takes to come back. And the time it takes to come back will be shorter or longer depending on the distance. Now the really important thing to note here is that it is there and back again. So the time is double what it would be, because the time it takes to get there and back is twice just the time it takes to get there. So if you have an echo or an ultrasound calculation, you need to find distance, you need to think logically about the time calculation that you're using. Ultrasounds can also be used for medical imaging. Here is my massive bump, here was my massive baby, and you can see the hard parts, the jaw, the skull, the legs, they are going to reflect the ultrasound much more than the liquid or the soft tissue parts. A sound wave is a longitudinal wave. It vibrates the air particles. And your eardrum in here will pick up the vibration of the air particles and turn it into sounds which your brain can interpret. The range of human hearing is 20 Hz to 20 kHz. When a wave is reflected, it is going to come in, meet the boundary, and then be reflected off. Our angle of incidence is always going to be equal to our angle of reflection. So we can always say that I equals R. Your normal line is in the middle here. It is a dashed line and it is drawn at 90 degrees to the mirror or the surface that the wave is being reflected off. If we have a sound wave instead of a light wave that is being reflected, we are going to get an echo. When you shine light into an object, sometimes some of it will go straight through and some of it will be reflected. Other times when you shine light into an object, none of it will go straight through and all of it will be reflected. At the point where it's all reflected, you have total internal reflection. And this only happens at the critical angle. A converging lens is shaped like this, and this is a shorthand for it. It is used to correct long-sightedness. It's going to produce a real image, and it's a type of lens used in magnifying glasses. I have made many videos showing you how to do ray diagrams, but just as a quick recap, for a converging lens, your first line needs to go from the top to the lens, and then on the other side through the primary focus. Your second line needs to go from the top through the middle. I should extend that line a touch. Your third line goes from the top through the focus until it gets to the axis, then it runs parallel with the axis and is going to be there. Then over here we are going to get our image formed, and that image is going to be upside down. So the top is there and the top is there. Your diverging lens is going to be curved in like this, and this is the shorthand. It's going to correct short-sightedness. It's going to give us a virtual image which is upright but smaller. Drawing a diverging lens, our first line goes from the top of the object to the axis, and then we need to backtrack through the focus on the same side. So I'm just going to draw a dashed line here, and then the line will actually go like that. And our second line needs to go from the top of the object through the middle, and where those 2 points cross, there is going to be our virtual image. Lots of different surfaces would emit and absorb radiation. Some will do it better than others. Over on the right hand side you can see the practical, one of the required practicals that I've done for you. Good absorbers are going to be dark surfaces and matte surfaces. Good emitters are going to be dark matte surfaces. Good reflectors are going to be shiny surfaces. The uses of radioactivity are quite varied, and what source of radioactivity you're going to use is going to depend on the half-life, and it is going to depend on the type of radiation. Gamma radiation can be used for cancer treatment and for sterilising materials because it is very good at killing cells. If it is going to be in a bit of medical equipment, we're going to need it to have a very long half-life. Beta radiation can't get very far, so it's just for things that need a short distance. For example, testing the thickness of foil that's being made or cardboard that's being made. If too much beta radiation gets through, then we know it's too thin. If not enough gets through, then we know it's too thick. For this, we need a long half-life because it's within industry. Whereas for a medical tracer, we don't want it to have a long half-life. We want it to get out of the body as quickly as possible. Alpha radiation is used in smoke alarms, and for this, again, we want it to have a long half-life. In nuclear fission, the breaking apart of atoms, we have a chain reaction. The first neutron is fired out of something and it hits our heavy radioactive element, whether that's uranium or plutonium. It doesn't really matter for this instance. It splits it, and we are going to get, the example would like you to draw 3 neutrons coming out. Some neutrons coming out, some radiation coming out, and some smaller atoms. The neutrons that come out can then go on and hit other nuclei. So it keeps going, and every single reaction releases a neutron which can go on and hit something else, which is why it's called a chain reaction. These nuclei, once they hit, they break down into smaller nuclei, release neutrons and radiation. Nuclear fusion is the process that takes place in our stars. It is going to be where nuclei fuse together to make one nuclei, one large nuclei. It's going to be combined with the release of energy, whether this is going to be light, heat, or sound, or all 3 in the case of our star. The value of gravity depends on where you are. The value of gravity on Earth is 10 newtons per kilogram, where on the moon the value for gravity is much less, which is why it looks like they're bouncing around on the moon. However, if you are falling on Earth, we can say that your acceleration due to gravity is 10 meters per second squared. Same number, different units. The reason that gravity is so much less on the moon because the moon is much less massive. It has less mass. Our solar system is a beautiful, varied and fascinating thing. Starting with the Sun all the way over here, we move through Mercury, Venus, Earth, Mars and our moons. The asteroid belts with some dwarf planets in, I'll come back to these in a second. Jupiter, Saturn, Uranus, Neptune and poor old Pluto down here, which isn't a planet anymore, it's just a dwarf planet. To help you remember the order, we have my very easy method, just speeds up naming, and then it used to be planets at the end, but Pluto isn't a planet anymore, so it's now my very easy method, just speeds up naming. If you guys have any other ways that you remember the order of the planets or anything else, pop that in the comments below because I'm sure loads of other people would love to see what you come up with. So poor old Pluto. Here it used to be a planet, it is now a dwarf planet. I did a separate video on why Pluto is now a dwarf planet, but our dwarf planets are here, 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 and here. I'm not going to try and pronounce some of those names because I'm very sure I will get it wrong. We have an asteroid belt in between Mars and Jupiter, and then another belt of large objects right on the edge. People used to believe that all the planets revolved around the Earth, but now we have moved to a heliocentric system and we know that all the planets revolve around the Sun. The galaxy that we live in is the Milky Way. And here you can see the Milky Way stretching across the sky. We are on the edge of the Milky Way, on one of the arms right on the outside. In the middle is a black hole. Here we have the life cycle of a star. It is going to start off as a cloud of dust and gas. And these are going to come together under the force of gravity, because everything has gravity, no matter how small it is, no matter how large it is, it all has gravity. And then we're going to be a main sequence star. Our sun is actually a rather small star in comparison to most of the other stars in the galaxy, in the universe. Lots and lots of them are much, much bigger. Now, depending on the size of the star, they're going to undergo two different things. Our sun, being a rather small star, once the nuclear fusion that goes on in the centre has run out of fuel, it is going to become a red giant, and then it is going to cool down into a white dwarf or a black dwarf. If it is a large star, much, much more massive than our sun, it is going to become a red supergiant. It's going to undergo supernova, and then the dense, dense core of that is either going to turn into a black hole or a neutron star. Now, our sun is a second generation star, because after this red supergiant undergoes supernova, what we are left with is a cloud of dust and gas. And that cloud of dust and gas can get together again to form a new star. And we know this is because the sun has heavy elements. Things like iron are present in the centre of the star, which means, since we were created from this cloud of dust and gas which also formed the Earth, that you literally used to be a star. You are a star. You are made of stardust. You are a star. You can tell people that. In the centre of a star, we have loads of hydrogen and helium. And they're going to be fusing together. This is nuclear fusion. Not fission that takes place in reactors that we have on Earth, but nuclear fusion. And we can see that massive amounts of energy is released. And this is energy as light and as heat energy. And if we were close enough, we'd be able to get the heat sound energy as well. When all of the helium and hydrogen nuclei in the middle run out, that is when our star's life comes to an end. Now, our star, our sun, is a main sequence star, so it's going to have heavy elements as well. They are going to be undergoing the same process, but the majority of elements inside a star, inside the majority of stars in the universe, are going to be hydrogen and helium. An artificial satellite is going to be something that we've put up into space to orbit the Earth, whereas a natural satellite is going to be something like the Moon, which naturally orbits the Earth. A satellite is just anything that orbits the Earth. They maintain their orbit around the Earth due to gravity. There is a key distinction between the terms speed and velocity. Speed is how fast you are going. Velocity is how fast you are going in a certain direction. So speed is going to be a scalar quantity, and velocity is going to be a vector quantity. If something is going in a circle, for example, orbiting the planets, it can be going at a constant speed, but it is not going in the same direction. If it is going in the same direction, it would always be going like that, in straight lines. So it is constantly changing direction, which is why you can have a change in velocity while going at the same speed. When we are looking at stars, we can see light coming from them, and the wavelength of light can tell us things about them. If the wavelength has increased, the frequency has decreased, it means the wave is being stretched out, it's moving away from us. When the wavelength is increased, the light coming from these stars is going to look red. We can say this is red shifted.
Sometimes the light coming from these stars might look a bit blue. When stars look a bit blue, it's because the wave is being squashed. It has a decreased wavelength and increased frequency. That means that the star is coming towards us. The majority of stars in the galaxy are moving away from us. You're going to get maybe a dual system where one is moving away from us, one is moving towards us, so one might show redshift and one might show blue shift, but the majority are moving away from us. And because they are moving away from us, we can make the reverse assumption that at one point they were closer to us, really close to us, or that at one point they were in the same place as us. And this is how redshift gives evidence for the Big Bang.